Indeed, it is tremendous to have a chance to welcome the next set of speakers, led by Joyce Wu, who manages the START.nano program of MIT.nano. We have asked a set of luminaries, people we tremendously admire, to join us. And Joyce, please come on the stage and tell us more about the next thing we would like to tell you about, and that is how to transition deep tech from academia to industry. Joyce Wu.
Thank you. So this session today, we'll talk about how we transition an idea into commercialization, particularly focusing on deep tech. Investment into hard tech is only a few percent by VCs, and the journey for hard tech is fraught with many challenges. An idea needs more time and resources to reach commercialization to become a product than one can realize at the time of inception. Ideas can be incubated within a large company, but most commonly they are through a startup. And there are many points at which a startup can fail in its journey to commercialization. First, one needs to find people who share your vision and bring it to the prototype or proof of concept stage. This is the first valley of death. The next stage to get from prototype to the advanced scale-up or advanced development or scale-up is another valley of death, where you need to find customers who see your product that can become a product. In this area, you also need to find the right market and the right solution for that customer. Then in the next valley of death, you have to find a partner or investor who will bank your idea to commercialization. These three valleys of death have attrition at each stage, and really a successful journey takes at least 10 years or $100 million. So how can we help startups in their journey with our toolset at MIT.nano? START.nano is an accelerator program to help fill in these gaps. Startups are climbing this mountain of hard tech, and we can minimize their needed funds by first giving them access to existing shared facilities like MIT.nano, and actually giving them a discount for the use of those tools. This allows them at that first stage, from idea to prototype, where they don't need to build their own lab and have investment capital to do that, and they can use our tools to build that prototype. Also, in the next stage, they can continue using our tools for development to reach those first customers. We have several startups in our cohorts. One is Citration, you'll see in the Startup Exchange. They didn't need to build their own lab, and their seed round was actually more like a Series A because they were able to build their prototypes at MIT.nano with less capital. And another example of a startup is Wicked Smart. When they realized we have an immersion lab, which has motion capture, they realized they didn't need to raise additional investor funds to build their own motion capture lab because they have access to the immersion lab. So this is actually our cohort for this year in the START.nano accelerator program. We have 13 startups and counting, and the acceptance rate was about 42%. And you can see they actually represent a large and diverse market segments. Here, a quarter of them are in biotech, and a quarter in climate tech and energy, and a quarter in materials. This broad area allows us to tap into many areas in the startup ecosystem, and we can support them with our diverse tool set at MIT.nano. And we actually even have a few software companies because we have the immersion lab. So this is a glimpse of all the startups that have been in START.nano since its inception in 2021. And some of them are here today at the Startup Exchange, Startup Showcase. And let's hear now from our upcoming speakers about their perspectives of how we bring technology to market. So first we have Marina Hatsopoulos, and she'll talk to us about her industry perspective of transitioning academic discoveries to commercialization. She is the board chair of Levitronix Technologies, the world leader in magnetically levitated bearingless motor technology, and the president of the Hellenic Innovation Network, which serves as a bridge for tech startups expanding from Greece to the US. She's a board member of Berklee College of Music, Alba Business School, and Athens College, and on the MIT Corporation Visiting Committee for the Department of Mechanical Engineering. She was the founding CEO of Z Corporation, an early leader in 3D printing out of MIT, and has served on numerous corporate boards. After Marina, we'll hear from Mark Halfman. He is the director of the Northeast Microelectronics Coalition, and he'll give us the regional and CHIPS Act perspective as we work across the local regions. NEMC is the network of over 200 organizations, including commercial and defense companies, leading academic institutions, federally funded R&D centers, and startups concentrated in 8 Northeast states. It was established in 2023 and funded through the CHIPS and Science Act. NEMC is one of the 8 regional Department of Defense Microelectronics Commons hubs, acting on a shared mission to expand the nation's global leadership in microelectronics and accelerate domestic semiconductor prototyping. Mark has over 2 decades of experience in commercialization and advanced technologies, having held leadership positions in public semiconductor companies and venture-backed startups in Boston and Silicon Valley. And lastly, we'll hear from Professor Dame Fiona Murray. So I have her bio here. She's the Associate Dean of Innovation at MIT and Professor of Entrepreneurship. She also is the Vice Chair of the NATO Innovation Fund, which is a VC fund with contributors from 24 NATO countries investing in critical tech. So now we'll hear from Marina, talking about translating deep tech to industry. Thank you.
Hi, great to be here. I'm going to talk to you about translating deep tech from academia to industry. And I'm going to make it sound really simple, like there are these steps and you just follow them and then you're good to go. But it's not really like that, and it's not that clean. It's all kind of messy. So I kind of broke it down into these steps, and I'll just go through them really quickly. So of course, it all starts with research. This is where there's an innovative scientific discovery. And the researcher might have a general vague idea of how it might be applied, but usually the application is somewhat vague, and that's fine. The important thing is that there's something that differentiates this technology from what has come before. The next is to patent it, and this is extremely important, and I can tell you from personal experience at Z Corp, we had core patents from MIT that actually blocked competition until those patents expired, and that was competition from HP. So those are really, really important. It protects you for 20 years from the date of filing, and you need those 20 years because it takes a really long time to develop new technology. But intellectual property also includes trade secrets and know-how, and so it's important to recognize those and protect those as well. The next step is publication, and generally, professors and researchers are incentivized to publish, and this is considered sort of an indicator of innovation, both for the individual as well as for the institution. And that's great to publish, but just make sure you get the order of events correct. You want to patent first and publish later. After you publish, it's too late to patent. The next is the proof of principle, and I'm going to show you what our 3D printer looked like when it was at MIT. It was not a pretty sight. But the point was they had taken out the magic. They had proven that the technology could work, and that's what you want to see. You want to get it to a stage that there's no more magic required and that straightforward engineering can kind of clean things up and make a reliable solution. The next is startup formation, and it's really important to think about the motivation for your startup. Why do you want to do this? Oftentimes, with a researcher, it's a passion for a particular technology. It could be to solve a specific problem, or in my case, it was a desire to kind of solve any problem and just kind of make the world a little bit better. Also, independence is a big factor. This was one for me as well, like wanting to be my own boss. The sense of teamwork and community that comes with a startup, or making money. And oftentimes it's all of these or some combination of these motivations. But the important thing is to understand your short-term and your long-term goals. Are you just trying to get it to a stage where you can sell it, or to scale it up to IPO, and make sure that your goals are aligned with those of your investors. One big mistake that I see often is that the researcher, the professor, wants to continue their day job during the week and then do their startup on the weekends, and that doesn't really work. Entrepreneurship is not a part-time job. Researchers need entrepreneurs. Entrepreneurs need researchers. It's a symbiotic relationship of beautiful codependence, and it's really important to respect what the other person brings to the table. The next step is understanding the market. So typically, deep tech research is a solution looking for a problem. And so to figure out what that problem is requires customer conversations, charting the competitive landscape, doing research at trade shows, reading articles, and reading annual reports. One of the mistakes I often see is the lab is a comfort zone for a researcher, right? And so it's always easier to do one more experiment than to get out there and find customers who you don't know how to find them, and you have to have this awkward conversation because you don't really know what you're talking about yet. But it's really, really important to do that. You need to understand, is the problem painful enough? How big is the market? And not to hold everything tight. You can retain your proprietary information, but still share enough information about what you want to do in order to get useful information from the market. And really, at the end, it's only a real product when someone will pay for it, so you need to understand who's going to pay for it and if they're willing. Obviously, when you're doing an innovative startup, you need to be doing something different. So you need to learn what's out there and do something different. You can't, the state of the art is not your end point, that's your starting point. So yes, you need to get your technology there, but then you need to advance it beyond that. And luckily, you have one big advantage, which is your ability to take a market disruption or create a market disruption and pivot. And when you look at a large incumbent, they have everything, right? They have customers, they have money, they have experience, they have distribution, they have manufacturing. They've got it all. The one thing they don't have is the ability to change course quickly. And so you've got to use that to your advantage, and typically that comes when there is a market disruption. It could be regulations, new regulations, old regulations that are going away, new technologies that enable some other technology, things like that. And so that's what you always want to be looking for. But you're always making decisions in the dark, and so, and that's good, you need to move forward, but as soon as you get new information, you need to remake those decisions, and that's why pivoting is generally part of your daily process. The next is building a team and culture, and I'm very proud of what we built at Z Corporation. We had a very diverse team of people with different interests, talents, experience, and we had a very argumentative culture in a very positive, non-toxic way, and I think this allowed us to make the best decisions. Then you come up with your plan, product specifications, value proposition, who is your customer, how are you going to find them? And the biggest challenge, I think, of all is finding your product market fit. As I said, you're a solution looking for a problem. Being different isn't good enough. You need to be substantially better at something that the customer cares about. But the good news is you don't need to be better at everything. So for example, at Z Corp, our parts were not, they did not have high surface finish or high strength, but our 3D printer was 10 times faster than any other technology, and that was something the customer cared about. Then you get to fundraising. So typically this starts with friends and family, then you go to angels. Typically equity crowdfunding isn't so good for this sort of thing. Government grants are a great source of funding for deep tech. And then obviously venture capital, and at a later stage, not just equity, but venture debt. And don't forget strategic investors. These can be your customers, your suppliers, anybody who has a vested interest in your success. And that can be in the form of an equity investment, an R&D contract, or what we did is we asked for very high customer deposits at the time of the purchase order. One big mistake I see is entrepreneurs underestimating the fundraising process. It's a big job. It takes dedication, time, research, and energy. You're faced with rejection and failure every step of the way, but it's important to take something away from every meeting and learn from each one. Was it the pitch or was it the business? Get some strategic takeaways. Don't waste those rejections. Then you get to the minimum viable product, and this is something that you're willing to show the customer, and you can see that our beta machine made a lot of strides since that first proof of principle at MIT. And this was something that we took to our customers so we could get feedback from the market and understand how we needed to iterate on the design to get something that they really wanted. One mistake I see is entrepreneurs seeking perfection, but if you wait until your product is perfect, you will have missed the market. So you just need to get something into the customer hands so that you can start to get feedback, because what you think might be close, but it's probably not exactly right, and so you need to get that feedback and hear from them. Finally, you get to sales. That's the exciting part. That's when you get money from the customers, and it kind of validates your business. But commercializing deep tech hardware has some specific challenges that make it much more difficult than your software comrades. You have manufacturing issues, cost of goods sold that needs to be controlled, quality control issues. We had to add 6 months to our development cycle, which was already 2 years long. Servicing equipment out in the field, which can be a huge challenge if you've sold machines all over the world. Generally, the time and the cost that you think it's actually going to be about 3 to 4 to maybe 10 times more time and cost than what you originally anticipate. And because of this, the investors know this, and so this makes fundraising that much more difficult. When you're in the muck, the startup fog, you have too many decisions to make, too many directions to go in, not enough information, and conflicting opinions. So your North Star always needs to be going back to your core technology, whatever it is that you've patented and protected. How does that create product differentiation? And now use that to help guide you toward who is your customer, what market are you going after, how should you develop the product, and where should you really prioritize your limited resources of time and money. Finally, factors for success are defensible product differentiation, a strong, diverse team, a healthy culture, and lots of customer interactions. Thank you.
Hello, everybody. Mark Halfman, Director of the Northeast Microelectronics Coalition. I do want to quickly thank Joyce for the invitation. I thought about this on the drive-in this morning. Joyce and I first worked together 16 years ago now at a early stage MEMS-based display startup, so thrilled to be able to join her today as part of her panel. As we get started, I thought Vladimir had an awesome quote. I actually wrote it down from his kickoff this morning. He had asked the question, how do grand ideas reach the world? And so what I'd like to do in the next 9.5 minutes now is take you through a regional point of view on that. So from the Northeast Microelectronics Coalition, how do we view that challenge, and what are we trying to achieve in an effort to help startups, innovators alleviate at least aspects of that challenge? So the NEMC Hub is a division of the Mass Tech Collaborative. For those that might not know, the Mass Tech Collaborative has been around for 40 plus years now, really focused on strengthening the competitiveness of the tech and innovation economies in Massachusetts. We are one of now 6 divisions within Mass Tech. The Innovation Institute really focused on early stage deep tech clustering, autonomous robotics, quantum computing, other initiatives of that type of size and scope. Center for Advanced Manufacturing really focused on how do they bring Industry 4.0 into manufacturing across the board within Massachusetts. Broadband, e-health, cyber. We are a bit unique within that infrastructure in that although the other 5 divisions are largely Massachusetts funded, Massachusetts focused from a regional perspective, we, the Northeast Microelectronics Coalition, are really focused across the Northeast, which for us is New Jersey, New York State, and then everything that we think of as the greater portion of New England. Also, from a funding perspective, we are funded through the U.S. CHIPS and Science Act. As I'm sure everybody's aware, U.S. CHIPS Act, $54 billion. We've all seen the large announcements, largely from the Department of Commerce funding TSMC, Intel, Micron, et cetera. What you might be less aware of is within that $54 billion is a $2 billion allocation being administered through the Department of Defense, specifically for the Microelectronics Commons, really addressing that second valley of death that Joyce referred to earlier in her presentation. So how do we really help innovative chips and chips-adjacent technologies make it from innovative concept to something that's a little more on its way to commercial readiness? Specifically from a Microelectronics Commons perspective, really focused around 6 key technology areas that you see in the bubbles there, but really spreading a wide range of applications from EW to secure computing on the edge, AI hardware, quantum, 5G, 6G technologies. Commercial leap ahead really could be called miscellaneous, so the catch-all for everything else, but to put a better nomenclature around it, commercial leap ahead technologies. But again, I think the key takeaway here is really how do we help bridge that lab to fab gap, if you will? How do we help bridge that valley of death? And from a Northeast microelectronics regional perspective, for us, that's really about how do we help innovative companies, innovative concepts, really regardless of where they're coming from. So whether they're coming out of university research, whether it's an early stage startup trying to get its footing, or even compelling ideas coming out of large multinational corporations that are similarly trying to figure out how they take next steps. For us, that really means how do we help those early concepts, whether it's at the white paper stage, whether it's a crude proof of concept, built out over a lab bench, something only an engineer could love. I love Marina's photo earlier from her early proof of concept, which is exactly what we think of there in terms of an early stage proof of concept. But from a Northeast Microelectronics Coalition perspective, how do we help accelerate, amplify, continue to move those types of technologies forward in what can be a very difficult investment environment, as Marina spoke to as well. So from an NEMC perspective specifically, we do see tremendous power in the Northeast region. I think it's important to note that we, the Northeast Microelectronics Coalition, don't staff our own team of design engineers. We don't run a test and characterization lab. We don't have a wafer fab. So our strength really does come from the capabilities, the capacities, and the commitments of our membership. And you can see that referenced here. I apologize. I should also note we are a relatively new organization. We just celebrated our 1-year anniversary last month, so I think this is tremendous progress for now. 13 months in to really a brand new seed of an idea, going from initial concept to now 220 plus organizations as members, 780 plus individuals within those organizations as contributors. You can see on the upper right-hand side, it's roughly comprised of 50% Massachusetts organizations, another 40% throughout the Northeast, and then the remaining 10% really around the rest of the US, from North Carolina to California and everywhere in between. I think the membership by category is also important because, again, when we talk about how do we help these early stage concepts get to some level of commercial readiness, I think it's important to note that you can see the breadth of membership we have from commercial and industrial entities to startups, academic researchers, other nonprofits and the like, which is really important as we work on how, from an NEMC perspective, do we become what we like to think of as the central point of curated collaboration? How do we help these innovators come together? How do we help mature the technologies, help move them from early stage lab environments to pre-commercial fabs to commercial fabs? As you can see, the core facilities that we help work with, really in tight collaboration with MIT.nano, MIT Lincoln Laboratory, and then spanning the other organizations that you see there referenced. And from a strength of our network perspective, you can see our first year funding, operations funding through the Department of Defense, US CHIPS Act referenced there, roughly $20 million. The vision is roughly that order of magnitude funding over the 5-year horizon of the US CHIPS Act. But you can see in terms of real value that we're bringing to the ecosystem, we've been able to leverage that investment, 40 million, north of 40 million now in private third-party co-investment. We announced beginning of this calendar year in conjunction with MIT.nano, Applied Materials, and the NEMC hub coming together to be able to provide or invest in over $40 million of new 200 millimeter wafer tool infrastructure into the MIT.nano facility, 40 million in Massachusetts state co-investment into our initiatives, 80 million plus in additional Massachusetts capital grants. And again, if you look at the overall infrastructure within the Northeast Microelectronics Coalition, it's multiple billions of dollars of regional assets that we're working to, again, leverage and help from a collaboration perspective to the benefit of startups and other early tech innovators looking to make that leap or bridge that gap from lab to fabrication. And in closing, what I wanted to do was just share our, let's say an initial success story in terms of what we're able to achieve, again, with an eye toward becoming that central point of curated collaboration. And that is another aspect of the Microelectronics Commons funding in its first year went toward $270 million of funding allocated across 33 projects within the 8 Microelectronics Commons hubs, of which NEMC is one. This is a project that started about a year ago, or a process that started about a year ago, an open call for projects through the Microelectronics Commons program, resulting in the 33 projects that were awarded just last month. One of the announcements was held here locally at MIT Lincoln Labs, announcing specifically for the Northeast Microelectronics Coalition, $38 million for the first year of execution on 6 different projects. You can see the names highlighted there, very brief descriptions of the technologies, but I think the 2 key takeaways are, although you see just one university, UMass Amherst, listed as a lead, all 6 of these projects are multi-organizational teams. So all of these projects have university researchers involved. All of these projects have federally funded research R&D centers involved, other startups providing technology. So these are all teams of anywhere from 6 to a dozen plus organizations coming together to help mature these IC-based technologies. And what I'll leave you with is really from the last bullet, not using it to highlight our successes versus the other 7 Microelectronics Commons hubs, because we're all in this together, but really to highlight the demonstrated success from the point of Microelectronics Commons, really the vote of confidence from the US CHIPS Act that the regional power within the Northeast Microelectronics, our 220 plus organization members, the way they were able to come together to propose the topics and receive more awards than any of the other hubs really is a testament to the power of the region and what we going forward look to continue to build on, whether it's to help collaborate and network startups looking for commercial support, whether it be university researchers looking for the connectivity on how they grow outside of the university research lab environment, or whether it be large multinationals that see a gap in their roadmap and rather than trying to address it internally or having their own tech scouts go scour the Northeast to understand what's out there, coming to us and enabling us to help them find the right technology researchers, the right startups, and get them to market much more quickly from that perspective as well. Thank you.
Okay, thank you very much. I'm acutely aware of the time, so I just want to make sure, Vlad, what time are we trying to, Joyce, what time are we trying to finish? Now I've got 10 minutes, but I feel sure that other people use more than 10 minutes, and I want to keep you on time, because I know that when you run conferences, it's quite tricky, and other people have a lot more detailed information to give you than I think I'm going to. But I think my job is to really talk a little bit more generally and try and put what I see as the extraordinary success of MIT.nano and the huge success that New England, the Northeast Mass Tech Collaborative has had in microelectronics, perhaps into a slightly larger perspective. And the way I think about this is that the university has to build a system that is going to support the kinds of amazing invention and innovation activities that Marina talked about. And then we really need our ecosystem to kind of step in and to do its job. And you might say, well, why don't we just sort of let everybody fend for themselves? And I think you've seen all the good reasons, both from the perspective of the individual entrepreneurs and Joyce's image, right, of those many valleys of death. I always thought we only had one, and now we seem to have about 5, and that seems quite treacherous. I suspect, Professor Bulovich, that is your fault, that we have those. And then Marina sort of brought that to life, I think, in this extraordinary way with those pictures that I think probably feel really familiar to so many of us. You know, when any of us walk into a lab, we see something that looks quite sort of chunky and clunky and interesting and sort of Heath Robinson and pieced together. And yet at the end, something extraordinary that transforms how our industrial processes work kind of comes out the end. And I would argue that it's because we have ecosystems around us that happens. But before I get to that, I want to show you this graph. So I had a debate about this graph with my husband this morning. He's an engineer. I showed it to him at 6 in the morning, and he was unimpressed. But I'm going to try and persuade you that this is an interesting graph. What this shows us is something that Vlad and I have taught about and talked about for many years. Basically trying to ask the question, how long does it take for an idea to sort of have some important innovative outcome, for an idea to go from inception all the way through to impact? And I think what you've heard already today and what you heard from Marina was that it often takes up to a decade. And what this is trying to do, this graph, it's actually based on an enormous amount of data, millions of data points, is ask this same question, the gestation. How long does it take for an idea to get from that stage of patenting all the way through to something sort of sensible? What this tells us is it takes anywhere from sort of a year or two all the way to 10, 12, 14 years. And what you might be able to see if you squint at it is on the left-hand side, the things where this happens quickly happen in a couple of years. Those are things that, these are all patent codes, transmissions of digital information. That means this is software. And none of us should be surprised that software kind of gestates, gets to impact in a few years. It's really efficient. On the other end, we've got, you know, production and refining of metals, methods of steam generation, gosh, mining, quarrying, fusion reactors. We shouldn't be that surprised that fusion reactors are all the way at the other end. And those ideas take upwards of 12, 15 more years to actually come to gestation. Somewhere in between, somewhere around 10 years, if you look into the data, you'll find things like semiconductors, right, quantum computing systems, and so on. Now, in the middle of the distribution, you get odd categories like dentistry. I'm not entirely sure why dentistry is sort of right at the middle of the distribution, but it is. And what this tells us is that it really is, some things just take time. And so what we know, and the way I think about this, which is really consistent with what we heard from Marina, is that it takes time and there's risk associated with innovation, particularly in deep tech, things that are physical, right? Sort of physical, deeply technical instantiations of our new ideas. And so the way I would talk about this is that ideas that are based on frontier science and technology, they have significant technical, market, production, regulatory risks associated with them. And those risks often cause us to have these valleys of death. Marina went through some of that architecture. That's mostly associated with hardware. And so you will hear people, particularly in this room, I think, talk about hard tech as opposed to sort of soft tech. Because I would bundle the life sciences into this, the word hard doesn't always work for me, and I sort of want to say soggy as well. And so then I'm trying to work out what word to use, but I'm thinking about things that are grounded in life sciences, material sciences, chemical sciences, as opposed to narrowly computer science ones and zeros. PitchBook talks about this as technologies based on tangible engineering. BCG calls them technologies of the future. I'm not sure that gets us very far. The word deep tech is a word that is reasonably widely used. Up the road, our friends at the Engine call it tough tech. But you know, you'll find this word around the place. And what we really mean are, as I say, things that are hard, that require very deep wells of capital and time to go all the way from idea to impact at scale. So how do we try to reduce the time and reduce the amount of capital. Because if we can do that, we can then ensure that more things happen, we have more impact on the world. The R&D dollars that we spend in our universities, in our economies, go further. And so what can we do to either compress the time or reduce the amount of capital that's actually required? Well, we get a little bit of a hint if we start to look at maps of where innovation activity, particularly patenting, hardware, telecoms and communications, is concentrated. You can see that innovation activities are highly concentrated. That doesn't mean that talent is concentrated. It doesn't mean that, let's say, creativity is concentrated. It means that innovative activities are highly concentrated. And you can see, not surprisingly, they're concentrated on the West Coast, the East Coast, an increasing amount that we're beginning to see in Austin and elsewhere around New York. This is a very uncomfortable political reality, and I could show you this for any country, but it is true. And you might say, well, why does that happen? Well, I think the reason it happens, particularly in this sort of deep tech, is because when we're trying to reduce the risks of deep tech, of these very complex technologies, of that idea to impact journey, we often do it by working in an innovation ecosystem. We do it by working in a specific place where we can find all the kind of supports that you literally just heard all about, right? All those support systems don't just sort of appear and are evenly distributed around the world. They are not evenly distributed across the US. Frankly, they're not evenly distributed across Massachusetts. And although we try to do that, they actually concentrate. And so by working in an innovation ecosystem, one of these concentrated, geographically bounded locations, when those ecosystems are rich in the resources that entrepreneurs need, like many of the individuals in this room who you'll hear from or have heard from, what do they need? You've already heard what they need. They need the kinds of human capital, the talent and the expertise, both to join their team, but also to help them in the form of the extraordinary technicians that we have at MIT.nano and elsewhere. They need funding, and not just any old funding. They don't just need somebody with a checkbook, although that's always nice to have. They want expert investors who've actually been through that journey, who understand the kinds of milestones, the pivots, the iterative experimentation that you heard about. And they need infrastructure. And this, I think, is the piece that we had underappreciated until quite recently, is how important the infrastructure is, because it's extremely costly for any given company to do that. And so what we find in these special places, like Greater Boston, like Silicon Valley, are a system of resources that are rapidly shared and exchanged by stakeholders who are in a sort of social network, who know how to find one another, so that each of you can do this sort of quickly. And what that lets you do is reduce the time and money to building your deep tech venture. And so the reason then, so for those things that take time, that have those wells of risk, that have valleys of death that need to be filled with money and infrastructure and talent, right? We basically know that we can fill those wells, we can cross the valleys of death much, much more efficiently if we are co-located with other people who are doing it, and we're in these ecosystems that are providing these sorts of resource systems to us. And so I'm not going to talk about that very much. MIT does a lot of this. This is my latest slightly mad bugle figure, which sort of says MIT has all these things that are trying to help all of you do this. Gosh, there's a lot of them, sometimes probably a bit too messy. But more important than just what we do on campus, although MIT.nano, I think, is an extraordinary additional resource that now has been developed on campus, is the fact that in the ecosystem, we have stakeholders who are together collectively providing those resources. And if I put myself in the shoes of the many, many entrepreneurial teams that I work with in the School of Management, helping them get their ideas from the lab out to the economy, who do they need to help them? They need the university, providing that early stage infrastructure like MIT.nano, providing the expert humans. They need risk capital providers. They're not evenly distributed across the US or economies. They're often here in these specialized places. But we also need corporations. And so partnering, having ILP here, it's really important because large corporations have access to key supply chains, customer channels. They understand the regulatory environment. They often have the balance sheet funding that can be particularly helpful in partnership. And last but not least, we need the government. You already heard what the state of Massachusetts is doing. It's in the context of the CHIPS Act, which is obviously the federal government. But the government can be very, very significant in supporting this expensive ecosystem-wide infrastructure It can do things like provide funding, everything from the SBIR and STTR to things like the vouchers that I know are extremely important in the semiconductor arena at the moment. And frankly, they can serve as lead customers, right? When the government says they want to buy something from you, like the next chip or the next piece of quantum computing, that can be a very powerful thing for a startup. And so we need these 5 stakeholders to come together. The last thing I'd say in my -1 minute is that I think that there are some quite complex global geopolitical dynamics that are shaping these things. So we can't really sensibly talk about this without at least recognizing a few things. One is within the US, I think that there's significant potential to amplify the support for deep tech, particularly deep tech in silico. I don't mean Silicon Valley. We are seeing this already in places like Austin, Arizona, Oregon, but we probably need to remember that this is not going to be evenly distributed across the US, and we have to accept that as a sort of price of doing this kind of business. That there are really important partners beyond the US, places that we can learn from and who want to learn from us. And I would point particularly in this domain to activity in Europe, places like Leuven with IMEC, Copenhagen, who are doing some extraordinarily interesting work in quantum computing, not just in the very famed, that rather sort of grey building is the Niels Bohr Institute, not just the research, but also the quantum foundry investments that Novo Nordisk is making. And finally, the geopolitical landscape, I think, means that we have to establish greater control over the stages of innovation. We need to think much, much more carefully about our supply chains. And frankly, the US, I think, is beginning to make a shift from what has been described as a sort of small yard, high fence, kind of America, putting everything in America. That's, I think, a quite inefficient approach. And you're beginning to see some very interesting movement towards what I would call shared gardens, which is engaging with allies and partners, so that we really think carefully about some of these global supply chains and pockets of expertise that can be networked together. But that is probably a discussion for another day. And so with that, Joyce, thank you very much.
Thank you. Thank you to our 3 speakers. That was an amazing talk, many talks about the different aspects of bringing an idea to fruition. And I'd like to invite our 3 speakers up for our panel with questions. So we have the pigeonhole where you can put your questions, and then people can upvote them, and we can ask, do you want to sit these 3? And I'll sit here. Yeah. Okay. So maybe to start, so you've talked a lot about startups, bringing deep tech into commercialization, and there are many ways a startup can fail. What are some advice, or what kind of elements would you suggest would be ways to be a successful startup or bring an idea to fruition? I think that's
well, it's a loaded question. I would say the number one thing is startups fail because they run out of money. And so always keeping an eye on cash and knowing where you are, what your runway is, and being on top of that is the top priority. Because if you run out of money, it doesn't matter how great your idea is. It just goes away and you won't be able to advance it. So it's sort of an uninspiring answer.
great.
Yeah, maybe building upon that, I think, given the timescales that we're talking about in, let's call it deep tech, especially if we're talking semiconductors or other technologies that require, it's called a third-party fab to manufacture your devices. Continuing to focus not only on the technology development, but also on your commercial or your customer development. Because as you move from small research facility, you can turn all the knobs yourselves, much lower cost. The cost as you move forward from a commercialization perspective, the cost of moving from MIT.nano, let's say to an MIT Lincoln Laboratories, to a global foundry can get exponentially more expensive. They will also, from the question of why should I support it? Why should I give you a discount? Why should I put my A team on it rather than some team that is perhaps less interested in really seeing you succeed? All comes from the corresponding customer pull that you can bring. It's one thing to just bring your technology to them and hopefully write a check that you can swallow and develop the technology. But if you bring a portfolio of tier 1 customers, tier 1 clients, whether they be commercial, industrial, government, that highlight as soon as you can build this in this quantity I'm in, as soon as you can get to this quantity I'm in, it just unlocks so much more potential, de-risks so many aspects of that, that I think critical to move, again, not only your technology development plans, but your customer development plans in lockstep with each other.
The only thing that I might add, if I may, is just that I think failing is okay. I mean,
Yes.
if we didn't fail sometimes, we wouldn't be taking enough risk. No investor assumes that everything is going to work, and we sort of know that's true, but it's hard to say that out loud. So I think the thing to do is to fail in a capital-efficient way, right? So that you set up the learning milestones, and I think, Marina, you talked about this, the kind of milestones, that journey, and pivot can sometimes mean pivot to stop. And so I think just being really clear-eyed about that is a very difficult thing for most teams, and a very important thing to try to do.
Yeah, and very hard decisions have to be made then, yeah. And I also agree about the customer fit, like you also, all of them, you mentioned that showing that you have customers really validates your use case. Okay, so we have a question here. What's the best way to access innovation that is coming outside the so-called innovation hubs, such as Boston and Bay Area? We could take the Midwest as a case example. How did you?
Yeah, I mean, I can at least take it from a Microelectronics Coalition perspective, or Microelectronics Commons perspective. So although there are 8 regional hubs that make up the Microelectronics Commons, and although we are regionally distributed, not surprisingly, fairly well aligned with the map that was shown earlier, but we aren't bound by those geographical regions. So even if you take a look at NEMC, for example, about 10% of our members are from outside the Northeast. And I think specifically to the question, some of those are startups in North Carolina. One is a startup in Arkansas that, frankly, doesn't have access to their local resources, wants to utilize the types of facilities that are available in the Northeast, want to start to plug into some of the end customer opportunities that are available here. And so they are more than welcome to join our organization and participate with the assumption that they're bringing valuable technology opportunities into the ecosystem. So there are certainly those opportunities for folks outside the Northeast.
Yeah, I mean, I do a lot of work in Greece, and it really doesn't take much in any of these ecosystems to get pretty plugged in pretty quickly, and showing interest, typically some place that's sort of not one of the hubs. They really appreciate outside interest, and they're very delighted to sort of show off what they've developed. And what you discover is that the difference between those non-hubs and the hubs is not the level of inventiveness at all. What the difference is generally the ecosystem that Fiona talked about, that whole infrastructure, and the overall culture of accepting failure and just going for it. So it's been really fun to see what's happening in Greece, and there's great stuff happening everywhere.
Yeah, and I would just add that I think that it used to be, so when we first started looking at this sort of whole idea of an innovation ecosystem, it was just a Silicon Valley phenomena that everybody looked at. People woke up to the idea that we do have such a thing here in Boston, particularly in the life sciences, but I would say absolutely also in sort of hard tech and semiconductors, that we are definitely seeing the rise of additional hubs elsewhere in the country, and I think that is being both supported by some of the government efforts that you've described, as well as those efforts sort of trying to go with the grain and saying, all right, we see this concentration of activity, let's say in Texas or Oregon, and let's sort of go after that. And I mean, I think you're exactly right, we see that in Europe as well, and that's definitely, so in the last 10 years, if you had been going to Munich for a period of time, you'd have seen reasonably little, extraordinarily large corporations, and now you see an incredibly vibrant innovation hub, particularly around things that sort of build on some of the traditional strengths that you have there. And so I think it's actually quite a positive outlook, but connecting into the hubs that exist. And one of the points about these hubs is they are open and welcoming, and I think that's really important.
And I think there are also hubs opening in the Midwest. There's definitely one in Chicago on the life sciences.
Yes.
Yep, and the START.nano program itself actually accepts startups from all over the country. So we actually have some in one we just accepted from Atlanta. So that's the same case with the NEMC. I think we're funded by the NEMC. So let's see, the next question. What advice can you provide to industrial companies to make successful and continuous relationships with deep tech startups?
I'll kick it out. Be open. As a serial entrepreneur myself, one of the huge biz dev challenges is, especially with a large industrial organization, is how do you get to the right person? You could spend months knocking on doors, trying to get to the right person within the right organization to start to have the conversation that you're really looking to have. And so being open to startups, helping them understand where that front door lies, so to speak, who can they connect with, how do they get quickly to the right organizations and start to have the dialogues that can really help form mutual collaboration.
I mean, so I've just finished writing a book about this subject that I think with my colleague Phil Budden, which I think is going to come out with MIT Press in April, although we haven't chosen a cover image, so any suggestions most welcome. I mean, the advice that I like to try and give is to imagine if you're a large industrial company, to try to put yourself in the shoes of the deep tech startup entrepreneurial team. And if you try and walk in their shoes, what you'll realize is that they are going through these milestones. They are trying to generate evidence of what works. They're trying to be capital efficient. Time is not on their side. So what that means is the thing that they probably don't want from you is your entire legal team to show up in their offices with, a 200-page contract. And so I think sort of trying to balance, the minimum viable paperwork for early relationships and conversations, and to be respectful of that fact, understand where the deep tech company is on their journey, and then really think carefully about how you can be a partner with them. What do you actually want from them? And what might they want from you? Again, it's probably not the lawyers. It may not be your HR department. It might, and it is your money sometimes, but it's often something rather different, I think, which is your insights into supply chains, your customer, right, a contract, right, much, much more practical and tangible, I think.
Yeah, absolutely. I mean, I think there are infinite numbers of ways that you can mentor and advise startups and get plugged into the ecosystem through incubators and accelerators and workshops and shows, conferences, things like that.
And where I worked previously, we also did a lot of strategic investment. So that's where we provide a lot of in-kind, like consulting and access to our supply chain. So that kind of thing also really accelerates their development. I think a startup we worked with said we accelerated them by 2 years because of the gaps that we could fill for them. Yeah. Let's see, what's next? How can a US-based startup with founders who are not in the US contribute to the CHIPS Act and participate in NEMC?
Yeah, so I was just rereading the question. In general, just like everybody else does, and I don't mean to be glib about it, but I mean, we welcome ideas from everyone. Although we're US CHIPS Act funded, or although a large significant aspect of our funding is US CHIPS Act, we're not entirely US CHIPS Act focused. Our vision over the coming years is to continue to grow, whether it's DoD applications, non-government applications, commercial applications, what have you. So I would advise don't let the fact that you're a non-US founder dissuade you from reaching out, from having conversations, from joining the hub and seeing how we can collaborate.
Yeah, I think that's right.
Let's see.
Part of what makes the US very special is that you have lots of people who are, themselves born elsewhere or whose parents are born elsewhere, and which is, I think the issue becomes visas. I mean, that becomes a very important issue and one that universities deal with, I think, different government organizations. Entrepreneurs find that quite challenging, but important to deal with.
Yeah, I think 1/5 of researchers in the US are foreign-born or something like that, and like 1/3 of entrepreneurs are foreign-born. So it's, the numbers work in your favor. And in terms of getting government funding, I work with a startup that has raised millions of dollars of government grants, and the founders are all born outside the US.
So let's this question about collaboration. What are the opportunities in the near term for US-EU collaboration on hard tech startups? What would that look like?
I mean, look, I'm happy to go first. And I think that there are some I mean, there are some definitely, I mean, there are a lot of, if you think about the ecosystem model, I think there's lots of opportunities from one ecosystem to another. And those, the sort of fabric of collaboration, I think often the universities are very good at that. They have very long-standing relationships with, for example, European universities. MIT has that with a number of major academic institutions. I think when you see large corporations, they often have multiple locations. I'm particularly struck in this field with a relationship with IMEC, who are in Leuven in Belgium, but who have a physical presence here. And so you see some very specific organizations trying to help make this possible because we're in a global market. The US, is complicated. If you're looking as an ally of the United States from the outside looking in, you're not quite sure how things are going to unfold. And so what you see is a number of collaborative relationships that might happen with the US on a country-by-country basis. The UK is seeing that partly because the UK is not in the EU anymore. And then there's sort of US-EU, and I think particularly there's a sort of interesting tension around the EU having its own CHIPS Act and sort of thinking of itself as entirely separate because they want European sovereignty over certain things, the US wanting the same thing, and then at what point do we collaborate? I think we've seen extraordinary collaboration, particularly with the Dutch, with companies like ASML, sort of acting as that fulcrum where you have to have the collaborative sort of architecture to help us. And NATO has been part of those conversations as well, because some of this is so important for global security.
What distinguishes between a deep tech startup focused on differentiation versus new efforts like SpaceX and Neuralink that create a new market?
Well, I will say Neuralink, there are other researchers and companies that have started that have been doing that for 20 years. So Neuralink is just more like a big promotional thing that, like, as if this is brand new, but it's not at all brand new. In terms of what distinguishes, I think you're always trying to find a hole in the market, so I wouldn't really view those as being different. There's always a market out there, and the market might be doing nothing, or it might be doing something different, but you're always, as an entrepreneur, looking for that hole. What's the need that's not being met by the current solutions, even if the current solution is doing nothing? And so I would say you're always looking to differentiate and create a new market niche, however big or small that niche may be.
The only other distinction I would make is actually whether something is so new that it's not clearly regulated. I mean, that would be, I think, a useful distinction. In the sense of, if you're trying to forge something that's so distinctive in the way you do something that the regulatory path is really, really unclear, I think that just layers on an additional layer of complexity and uncertainty. And so, some of the very early activities in, say, autonomy, was completely unregulated and nobody really knew what you were allowed to do and nobody knew how to test it either. And so I think that just adds, but I think that's different than a new market. It's sort of, is it in such a new way that we don't know how to regulate it? It just makes any investor have more of a headache, I think, than we did before.
But I think it is a good point, and you agreed it shifts it from the market side, let's say, to the underlying enabling technology side. But I think there can be a differentiator on that technology side, one of which would be if you're building within an existing technology set or on an existing technology platform, your path to market from, let's just say, a testing characterization perspective is going to be fairly well known. You know what your HTOL, your high temp operating life requirements are going to be. You've got those models, you know how to apply them. Versus if you're building from a brand new technology platform where that physics might not yet be understood, those failure mechanisms might not be understood. You do now have another set of hurdles to overcome to get to market, which is to, one, understand what they are, and then two, demonstrate that you understand what they are so that from a technology adoption perspective, the customer is willing to take that incremental risk, in theory, for the incremental reward that you're giving them in return.
Yeah, I think to compound on that, the more innovative your technology, the longer it takes to educate your customer on your solution. And I mean, in our early days, nobody knew what a 3D printer was. And so you've got to start at ground zero. Like, why would you use a 3D printer? What's the benefit? Yeah, it's cool and sexy, but does it really matter? And yeah.
Yeah, and I mean, I remember, every class that Vlad and I have taught, I think, Vladimir, you know what I'm going to say, which is that, there are times when you say, well, if I'm developing it, I've got new technical risk, I don't quite know how this is characterized, there's new markets, new regulation, which I just described, but sometimes it's not even, the foundry doesn't exist, right? We don't actually know how to manufacture something, and so I actually have to invent an entirely new manufacturing process as well. And so when you compound each of those things, you end up with more and more risk that you're carrying. I think makes it more complex.
Definitely. So I think that was the last question. Thank you for all your questions. And we're all going to be here for some of us are going to be here for today. So thank you very much for our speakers today and the great panel. And so here is our startup showcase in the next room. So we have a few selections from our current cohort and some previous cohorts. So please check them out. And I guess it's time for lunch. And thank you again so much.
Thank you.
Great talks.